All right, continuing on with week 12, I am going in an excess amount of videos. Whoops, let's go back up to this one. All right, so this one is from Bedford and Fowler. I do have the solution manual to this. And once again, that's a little bit different from our book. It's not a vibrations book; it's a dynamics book, but it's the same type of problem and should have come up with the same result. Which could be frustrating for the professor when he sees the solution manual do a totally different thing. But that's okay. So this mass weighs 50 pounds, which is really the weight, is 50 pounds. And the spring constant here is 200 pounds per foot. And we have a C, damping coefficient of 10 pound-seconds per foot. And if the base is subjected to an oscillating displacement of amplitude right there, right? So this thing is actually moving xi with an amplitude, right? So that, for us, we'd be calling that y. So I'm going to stick to the y here. I've gone back and forth this semester. I apologize for that. And then, so an omega f is 15 radians per second. What is the resulting steady state amplitude of the displacement of the mass relative to the base? Okay, so this is a key word in choosing our equations and our procedure. I messed up previously and didn't think my way through this thing. Okay, so this is really a relative motion, and so we're going to say that we're looking for z, because it's just let's say this correctly. It is, remember that z was equal to x minus y, right? So the form of the equation, we're looking for the one where we have a relative motion, similar to a vibrometer. You can even consider this to be a vibrometer. So let's check the thing out and do what we got to do. So first things first, find the natural frequency of it. And remember that these are US units, good old US of A. And we could use the weight, but we needed the 32.2 to turn it into the slugs. And that way the units will balance out. We get 11.35 radians per second. And we can find with that, we can find the critical damping coefficient of 2 times, you remember, need that 50 divided by 32.2 for the mass, and then the 11.35. And we get 35.25. And these are pound-second per foot. And then we can get squiggle, because we have C over CC. And so we have a 10 over 35.25. So we end up with 0.2837. And we can also find what R is with omega. Oh, why did I write a 3? I don't know. Omega F over omega N. So what do we got? Where do we get omega F? Right up here. Oh, we also wrote it right there. 15 over 11.35. So, and I can also just look at my page because I have it written down right here in front of me. 1.322. All right, and now, because this is motion relative to a base, we will use the equation that goes z is equal to y times r squared over square root of 1 minus r squared plus 2 squiggle r whole thing squared. So the y is going to be, we can just keep this in inches, right? So it was given to us in inches, so we could report the answer in inches. And so because this is going to be unitless over on the right-hand side. So we got 1.322 squared over square root of 1 minus 1.322 squared plus 2 times 0.2837 and then 1.322 whole thing squared. And what we end up with is 16.50 inches. And that matches up with the solution manual, which is a nice thing. We could be happy for. And there was much rejoicing. Yay! And we'll do another video. That was only 5 minutes, by the way. Boom.